Okay, so this talk it's quite a general talk. So it's on integrated real-time auto processing at Diamond, and it's not based on any particular technique. We're just looking at how we can take standard tools and resources that we have at Diamond and glue them together to produce a nice kind of generic system that can work across multiple experiments. Because resources are tight, so if we can reuse stuff, that's a really good thing to do. And if I can go on to the next slide, also a really good thing. And reuse and general things are really good. And with this in my mind, I thought, well, maybe I can make a general introduction slide that I can then reuse through all my talks throughout my career, because reuse is good. So I spent some time thinking about talks that I give, and I spent longer than I would have if I just made a nice specific introduction slide. But in the end, I made an introduction slide that I think I can reuse and should work for this talk. So things used to be both harder and easier, yeah? Experiments were harder, detectors were smaller and slower, we didn't have such good hardware scanning, but users could just take their DAT file, their stack of TIFFs, copy it onto their laptop, use ImageJ, Fit2D, Dawn, process their data, carry on their science at their own rate. They were quite happy. But now scans are easier, yeah? Detectors are super fast. We can collect a lot of data, do hyphenated techniques like Xrd Tomography, these kind of things. So experiments have got really easy. We've got brilliant automation, but they're also harder because we now generate so much data, and we generate data automatically for users that they don't necessarily expect to find in their visit directory. So that's got a lot harder. So I've made a nice reusable slide that's introduced my talk. Is it a good slide? No. Will I use it again? Also no. Because there are challenges in reuse, yeah? As with any facility software, there are challenges. Diamond's got many beamlines, and we kind of do hit the four V's of big data. We've got volume, we've got velocity, but we're built on a relatively uniform base. So most of the beamlines are running the Epics stack for controls. They've got GDA on top. We're writing data into HDF5 using Nexus tagging for the metadata. So it's a nice uniform base on which we can build. But as you move up the software stack around science, you do start to branch out quite a lot. And the uniformity in analysis is a lot less. So Xrd is not SACS, it's not PDF, it's not X-ray emission spectroscopy, it's not XRF. And sometimes the best code for these techniques is one that you haven't actually written. Someone else has written it for their use cases and you want to use it. And the faster you go with these experiments, the data is not necessarily formatted in a way that you as an analysis person might want to access that data. So you've got to do more post-processing to get it into a form that's nice and friendly for the users. Otherwise, you're just dumping a load of hard work on the beamline staff and users when, well, they bought a new detector and a new stage because they thought they could do better science from that process, yeah? So to do this, we really had to think about what was the experience we wanted to give users now that experiments are getting faster and more complicated. And really, we want kind of like an MX experiment. So the user comes in, they start their scan. The starting of the scan triggers real-time auto processing. It gives them live feedback so they can make decisions on, if they've started a 2-hour scan, do they want to kill that scan after 10 minutes because they're doing radiation damage to their sample. We want to give them this information so they can make better decisions. Then at the end of the scan, or when the live processing finishes, we want to do more things for them, because the more information you can give users, the better they can use their time when they're on a beamline. Have I measured this sample enough? Am I confident that I can get the publication quality data I need from this scan that I've done? If so, okay, I'll take that sample off and move on to the next one. The more things you do for people, the clearer you need to be about what you've done. So information management systems where you can say, we've done this scan and then we've processed it in that way. Here's the parameters that we've used. This is why we've done it. Are all really important systems. And these are kind of mixed in with the provenance so that users, when they get home, they've got all this auto-processed data. They know what you've done to generate it and they're confident to use it in their publications and decision-making. Because just generating files and dropping them in the visit directory is not good enough. They need to see what you've done and why you've done it. And ideally, if you've got the resource and the infrastructure, you should be then letting users reprocess that data through the same systems, because well, if they've supplied you some start parameters, they might want to change those parameters and reprocess the entire visit, and also use those parameters for all future scans. So pretty much like the sort of things they do at MX. And we're not starting from nothing. Yeah, we've been running Facility for a long time. There's a lot of available infrastructure we can use. We've got acquisition systems, we've got access to data and metadata, we've got compute clusters. So really, we just need some little things to glue things together, like systems that launch auto-processing, laboratory information management systems like I/B, and nice kind of middleware open source platforms like ActiveMQ that allow this kind of cross-process communication to work. So we have a system that works across many beamlines, and behind the scenes, kind of looks like this. So the users will be setting up an experiment in their GDA client user interface, which runs on one system. The GDA server is running on a control machine. The user is not accessing that directly. So they configure their scan. And as part of their scan, they might be doing a grid scan. They'll set up the usual parameters, but we have an also processing launcher with a REST API. And the REST API will tell the users, you're on beamline X12. Here's the auto processing available for you. Here's the parameters that you need to configure. Here's what type of things they are. Feel free to configure some auto processing parameters to include with this scan. So they can do that, they launch the scan. So the GDA server sends a message onto the ActiveMQ broker when a scan starts with some basic metadata. The auto processing launcher picks up that metadata, goes to the raw Nexus file, pulls out even more metadata from the Nexus file, writes into the I/B database. So we've got some basic metadata in information management system, which is then viewable through the sync web user interface. At the same time, the GDA client gets the ActiveMQ notification saying the scan started, here's a file. Because of kind of POSIX restrictions around Swimmer, it can't read the data directly, but we have a data server that's running on a GPFS mount, which can. So the GDA client talks to the data server, asks it for the Nexus structure or any useful data sets that it wants to display to the user. And so the user can start to see the raw data going. So after that, when the scan starts and the auto processing launcher has decided what it needs to do, it just forwards the information to Zocalo. Rich has talked all about Zocalo, so I don't need to really dwell on it. But Zocalo kind of stores the configuration around what processing there is available, what parameters they need. It talks to I/B, so information about the processing will also appear in the sync web user interface. It launches the auto processing applications on our cluster, so I can encapsulate the auto processing from our resources, which is really nice. Then the auto processing runs, it talks back to the ActiveMQ broker, which can then tell the GDA client that there's more data in Nexus files. The GDA client talks to the data server, says, please give me information about the process data, and we've joined our loop quite nicely. So how does this look on a beamline? What's the user experience from knitting together all this infrastructure? So I'm going to take the I18 focus XRF beamline because they're quite an interesting beamline. They do XRF and Xrd with two quite fast detectors, but they also do lots of hyphenated techniques. So they'll do XRF and Xrd tomography, they'll do Zane's mapping. They have an optical microscope, it's all very nice. They get some very prestigious users, and we like them a lot. So when you go to I18, you have a very desktop-like Daiquiri experience. So we're running, Eclipse, RCP, desktop applications, but you have a stream of your on-axis camera. You can define a region where you'd like to do your grid scan. You can also have some user interface. So this is automatically generated user interface saying, I want to do windowing on these elements. I'd like to use this kind of window width. And we can pop up bespoke user interface based on type hints that we kind of get from the auto processing REST API to say, well, actually, this string is really a list of elements. So could you pop up a periodic table to let them select the elements they want to use? So they configure the area they want to scan, what elements they're interested in looking for, and press go. When they press go, they see the raw data file appear in the list of, let's move the slide forward. They see the raw data file appear in the list, as well as any data sets from that file that they might want to see. Once the auto process, and they also get a sort of bare bones record of what's happened in the web interface. So if they've got sync web open at the same time, they can see, okay, a scan started on my beamline, but all it really says is some very basic information, and that some Jupyter auto processing is about to start. Then the auto processing kicks off. Via Actor and Q, they get the notifications. Swimmer allows us to read the data. So they get another file appearing in the window. They can click and look at different elemental maps, whatever they want to see. The sync web status still shows the same because the Jupyter auto processing is still running. When the scan finishes, the map's complete. They can carry on investigating the data in the same way if it's static or if it's live. And they also have more metadata and information in SyncWeb to give them a better kind of record of what's happened. And you can see the auto processing now has a green tick because it's finished and all is good. And if you expand the auto processing section, you can see there's some attachments. So we ran this processing in Jupyter. We've got the notebook, we've got HTML render of the notebook. We've also got a record of the Nexus file that's produced. And if you look at the top of the notebook, then you see there is a list of elements and parameters which should be the same as what was recorded in the GDA client at the start. So there's some confidence that they've given us some metadata and we've propagated it correctly through our chain. And here's the provenance to show you everything has behaved as you expect. So there are a couple of key components to make all this work together nicely. Swimmer is absolutely critical for us. So we use Nexus tagging for the metadata. We could use Swimmer because we can read that metadata back out. There are two things we use for Swimmer live processing, either Dawn or Swimmer Tools, which is a little small Python application that basically lets us stream NumPy arrays out of a HDF5 file as it's being written to. But to get this to work at a kilohertz or 100 hertz through diffraction detector, it's not completely trivial. So our writers are using BLOS compressed direct chunk write with potentially parallel writers stitching it back into a VDS to get the right performance that they need with these high performance detectors. And to match that, we're using direct chunk read, then we're decompressing the data actually in Python side rather than letting the HDF5 library do it. Because of the systems that we have, the fluorescence detector is writing at 1 kilohertz and we're reading at 1 kilohertz. And it turns out GPFS is not particularly happy if you try and do that kind of read and write rates. So there's certain issues to be worked around. VDS is also an issue for us because the VDS doesn't actually expose the chunking. So you can't do direct chunk read on a VDS. You have to navigate your way to the source data sets, which kind of loses the point of the VDS in the first place. But with all this stitched together, we can actually read the data out at basically the same rate that it can be written. So we're currently working on sort of benchmarking using direct chunk read against BLOS decompression. Then we pump the data into PyFile on the GPU to try and do real-time XRD reduction for these type of experiments at the rate that the detector, at the maximum rate the detector can run at. So another main bit of glue is our auto processing launcher, which has the imaginative name, the GDA's overlay connector. So it subscribes to the GDA scan messages, unpacks metadata from Nexus and records it into ASPIB in the appropriate places, determines whether there's any default processing based on the Nexus structure in the beamline, and then unpacks any requested processing, sends it all to Zocalo to be done, and it exposes these processing types via REST so they can be configured by the client. ASPIB, SyncWeb, and Zocalo are another, basically, a unit that we have directly stolen from OX because it has some really useful features. ASPIB is a very rich database structure for structural biology information management, but there are some very generic tables that allow us to record a scan was done. Here's the file that was produced. That scan was auto-processed. Here's the parameters used around auto-processing. And that's exactly the sort of basic information management we wanted to build this system. So we didn't need to reuse anything. SyncWeb was useful on top of that because it gave us the authentication authorization access to ASPIB. So if we recorded the records, people could actually see them and only the things they were supposed to see. We get Zocalo for free with the stack, so we may as well use it to run our auto processing because it encapsulates ASPIB in our compute resources for us. Inside Zocalo, Richard has talked a lot about that, I won't dwell, but we largely run the application in wrappers. The data goes from HDF5 to HDF5, and we can run all sorts of things in these wrappers. The best tools that we run are Papermill and Jupyter because it gives us an access to a massive Python ecosystem of code that people have already written that we can just reuse. So my favorite wrapper at the moment, which is the one that the example of my team was talked about, is the wrapper that uses Papermill. So Papermill is something that will inject parameters into a Jupyter notebook to allow you to rerun it. So the Beamline, us, or users can write template notebooks, and Zocalo will take parameters from the ICE/B database and inject those parameters into the notebook using Papermill, leaving us with a Jupyter notebook that is ready to be executed. A reference to the environment you want to run that notebook in is also stored in the ICE/B database as a processing parameter. So we can then tell Zocalo, please launch this notebook using this environment, and it should all run nicely. This wrapper broadcasts the results back to Zocalo for either further processing or for showing in ICE/B. And because it's a Jupyter notebook, we get quite basic visualization and provenance, but it's absolutely better than nothing. The nicest use case we've had for this on I18 recently is Xrd Tomography. So they are an XRF beamline. So the scientists really like spectroscopy, but they've got a good XRD detector, microfocus, so they can also do Xrd tomography. But it was quite an effort to process this data the first time they started doing it, because the Xrd tomography scans are pretty big. You've got to reduce the data, and then you've got to pipe that data into a reconstruction, then you've somehow got to visualize the reconstructed XRD data to see whether your science is actually working. So by using this system, we now, for every scan of stage X and theta they do, we live reduce that data with PyPhi. We take the live reduced data from PyPhi and we post reconstruct that with ToloPy in a notebook, which gives us a nice reconstruction that they can look at, a Jupyter notebook. And then because we're just running, we show them a simple reconstruction of the sum of the diffraction data, but that doesn't really tell us much about the structure. We then just take that data and pipe it into PCA, which kind of separates data based on the variance of each kind of part of the signal. I mean, this is not a publication PCA result. This is not the sort of multivariate analysis that I would do if I wanted to publish a paper on PCA, but it does give the scientists at least some indication about where different components are in their images. So they can go, okay, the scan's finished, I've got the reconstruction, and I can see there are structural differences in the sample looking kind of like the thing I would expect. So I'm pretty confident the quality of that data is good enough that I'm going to move on to the next part of my experiment, which is pretty much exactly what I wanted for our use case. So to conclude, to deploy anything generic is pretty complicated if you want people to actually use it and like it. You do need lots of infrastructure for very high performance experiments. Making results easily findable is critical, and it's really nice to see all the work that people have been doing on data catalogs and these kind of systems here. It's a really nice conference for seeing what tools you can steal when you go back to your own facility. But yeah, provenance and information management systems are key, but there are really good open source tools out there if you want to use them. So I've just got some screenshots of a variety of different techniques that we've deployed this on. And also, in exchange for the typography screenshot, I had to say we have a typography workshop looking at TypeI at DLS at the beginning of January, if anyone really likes typography. And thank you for listening.
Thank you. And for one question. I had one. I mean, it looks really good, yeah? So what's missing?
Well, we're going to rewrite it with Fidelity.
Okay.
Because, I mean, what's really successful about this is the modularity. So having a small thing that does its one task and then passes off the rest to another thing. And in the middle of that, we have the GDA client and the GDA server, which do a lot of things. And ICE/B, compared to some of the data catalogs we've seen for physical sciences, the metadata searching is not what we want. So I think the overall structure and how things work, that's great. But we can improve everything by swapping out different components. And as more diamond things come onto stream, we'll just keep improving it. Yeah?
It looks really good.
Thank you.
Okay. Thanks again to Jacob. And